So MROS. MROS is about Metacontrol for ROS2 systems, and I'm going to explain you briefly what Metacontrol means and what are our plans in ROS2. So very briefly, some motivation for this strange one-year project. Autonomous robots. Let's go out of the comfortable factory floor and think of robots that have to perform autonomously in more complex environments. So going back in history, we have some good news in the past. It was for example, ROS. ROS was a great news for the robotics community. It was going to make robot abilities boost in all areas, from the household to inspection, underwater, drones. We're gonna be solving everything in robotics, thanks to the ability to reuse and exchange marvelous components, right? And it was quite a boost in robotics more than a decade ago now. So that's part of the acceleration in robotics we have seen. So that was very nice, great news. Some intermediate news, a bit more personal. So we used ROS to win the Amazon Picking Challenge some years ago. That was a robotics challenge, similar to those at RoboCup, with a bit more of an industrial flavor. At warehouse, the challenge was to pick and place objects in Amazon shelves. And we could create a very effective and efficient system just using off-the-shelf ROS components and our ROS industrial expertise in Delft. So this is promising, this was promising, but then we also got some not so good news in the DARPA challenge, and everyone realizes the complexity of this, so it's a bit unfair to just show a robot falling in front of an open door. They were actually capable of doing quite some stuff, but this is just to represent how complex this is, and the distance we still have to cover to have robots performing safely and robustly anywhere, anytime, or more concretely 24 hours when you deploy robots in critical applications. And also, and I wanted to point out, these robots, or most of them, were actually teleoperated with an entire team of engineers supervising their operation. So this is not the scalable robots that we were aiming for, that were gonna solve the tasks for us. Actually, this is good news in the sense that look how many new jobs are being created just by one robot. Just kidding. So we need to solve this because we cannot produce all the, well, these many engineers for that. So what's the underlying cause of that? This here is the control architecture we use in the Amazon Picking Challenge. And this is just, well, it had over probably 20 components just for pick and place. So you can imagine the complexity of this kind of control architectures. And in these architectures, we end up embedding a lot of assumptions and cases to cover for system errors, task contingencies, and the regular task flow, which is actually the one not in red here. And we end up coding a lot of these exceptions or assumptions here. And that's actually the difficult part to scale for more complex applications. So this is the motivation for the Metacontrol of ROS systems. So I will briefly point to the solution we are aiming for in this project, what practical objectives we are targeting, and what is the technical approach we have. So what's the vision of Metacontrol? The idea is that when you create a system, you depart from some mission requirements, then you design your system, and in here we are only going to focus on the control architecture, meaning your ROS graph in our case, and you put that to operate. And hopefully, if everything is correct, and if the uncertainty at runtime is what you expected when you designed your system, then the system behavior matches your mission specification, your requirements. But all of us know that that's rarely the case, and you need to revisit this. And when you are programming an industrial application or something that you can test and check again and adjust to the environment, well, you just go through this loop, through this sequential process of testing and reprogramming your architecture. But when you have autonomous systems performing in very uncertain environments, you need to cope with this without going back with the people to the development stage. So we need the system to be able to adjust and redesign itself for that uncertainty. Not all algorithms for localization can cope with any situation. All of a sudden you have reflections, your sensors don't work, and you are lost, basically. And you have solutions here, actually. So if you think back about that problem, you can probably code a solution. But we need the system to be able to do that on its own. So that's the core vision here. How can we implement this adaptation loop? That's the key. And actually, in this project, we are going to be exploring how to use a model-based approach to software development, because that allows to obtain a certain description of the system that can be used to redesign it, basically. So the idea is to use at runtime these models to reason about how to redesign the system. And that's what we call Metacontrol, and it's basically the self-adaptation exploiting these models. And in MROS, in this project, we are going to be based on previous work that we have actually started developing during ROS-I, and now with the great support of RobMoSys, for which I will point later to the presentation of Dennis that will explain in detail the RobMoSys approach. But basically, this, for the first time, is providing us with a framework to elaborate properly these models to make them reusable. Not only for the design of the system, that is very important, but in this project we're going to explore the ultimate value of that for runtime configuration. This is just for you in the video to be able to look into further information. So in these publications, I explain in more detail this concept of Metacontrol, how you can do it using ontologies, actually, automatic reasoning, and the framework, the model-based systems engineering framework this modeling approach is based on. So I will not go into details now. You can look at it. So MROS is actually not a ROS-I FTP, but a RobMoSys ITP, which is the same concept. And it's very nice that we are cross-fertilizing each other here, because we have some ROS-I FTPs on model-based approach by RobMoSys partners. So the idea, MROS is just the result of this great collaboration of these European projects towards an European industrial digital platform for robotics, and it involves the coaching and the support of RobMoSys, of partners that are from ROS-I and from the OFERA European project, with Bosch involved. So we are basing our approach in the RobMoSys approach of composable models and software for robotic systems. It's a model-driven approach, and I'm reusing here RobMoSys materials, I think in this case by RobMoSys coordinator, Waskar, explaining the value of the models in the development of software systems. Depending on how complex they are and in which moment of the life cycle of your software they are used, they can help because they can abstract, they allow for reusability, they allow to predict better what your software is going to do. They allow to automate, for example, configuration of your software. And here, we are going to be using it for the extreme ultimate case of making the system fully autonomous by exploiting these models. So more about this whole model-based approach that I think has a lot of value for the ROS community in the next talk by Dennis Stamfer. So what concrete objectives are we targeting in this project? We are going to be developing these models or meta models for reliable robot skills by creating this self-adaptation, architectural self-adaptation at runtime, which basically automates what I was pointing before in red. All these system error handling, task handling, and task contingencies being automated and dynamically handled by the system through reasoning that can be reused from one application to the other, and that's the key. So we will be implementing this for a very concrete use case. So we look into ROS2 because that's a great platform. ROS was good. ROS2 is great because it has some additional nice features. So it has managed nodes, for example. So it has some of the infrastructure that is needed for our application. And the ROS2 navigation is probably one of the most advanced and mature stacks in ROS2, so we will be focusing on that one to implement our approach. So we will be endowing that software with this Metacontrol ability to adapt. Sorry. And finally, well, this is maybe not that interesting for the people here unless you are really into automatic reasoning and ontologies, but we will demonstrate how you can actually get some value as a developer of using these abstractions into ontologies with nice properties for validation and verification and nice tools to do that automatically. So we are going to develop a pilot for navigation. So we will develop a branch of the navigation stack and hopefully contribute into the navigation 2 stack. We will create 2 demonstrators with varying task requirements, so one in a Tiago platform and another one in a Bosch consumer mobile robot. And we will be focusing on improved reliability and autonomy of these platforms. So we are looking into having a clear impact into composable components. So we will show how components in this for navigation can be composed at runtime. We will be looking into switching and replacing those components when one fails for a variant or an alternative one at runtime. We will be looking into reusability. So actually our Metacontrol solution will be applicable not only to the navigation stack, but hopefully later to move it and to any other robot control architecture. We are aiming to have an impact in the reliability and the quality of service in these robots, and into standardizing the use of models and interfaces for managing ROS software at runtime. So we will evaluate this impact through KPIs defined around the availability of the system, the engineering effort to develop this additional Metacontrol level, and cost in terms of cost and time. And I'm not going to go in detail on all these KPIs we are going to use to measure it. So very quickly, our approach. So you have your ROS graph for navigation here. So we want to create the Metacontrol on top. How are we going to proceed? Well, first of all, navigation 2 in ROS2 has behavior trees as the coordinating part on top of the system, and it allows for plugins to create your own version of that behavior tree. So we will be using that to have a special behavior tree navigator for navigation to systems that is actually Metacontrol. And which kind of models we are going to use for this Metacontrol to decide how to configure the system, for example, when a sensor fails, or to obtain different safety properties when navigating through a corridor or through a crowded room, for example. Well, first of all, we need to have a model of the behavior. So we will be using RobMoSys models for behavior, which are some of them already developed for behavior trees. Then we will make use of the ROS2 node lifecycle model to be able to manage the nodes in the ROS graph. And moreover, we are going to use the system modes that Bosch is developing in the Opera project to abstract from this life cycle into the entire configuration of the system. What's the status and what's the configuration of the system, so as to be able to manipulate the system at the configuration level. So this provides a nice level of abstraction. But we have two views here of the system. We have the behavior view and the structural view, the configuration view. So we need to, we will be integrating here to manage the system, the associated mode manager and monitor that Bosch is also developing. And we need a model in between to relate the behavior and the configuration and the architecture of the system. And that's what we will reuse, that we have been developing in previous project and also in ROS-I. That's a functional architectural model, basically, that relates the system behavior and the system configuration. So together with these meta models defined, we will be able to abstract the appropriate model of the system and inject that in an ontology format so that we can reuse automatic reasoners that can be validated and verified on the rules they are using to configure all this. So of course here there's a lot of additional interfaces in between these three modules that we will be defining. So the project just started last month. And of course we will be basing our modeling approach in the RobMoSys meta models. We have a collaborative effort to define which kind of models are needed to properly specify robotic systems. So very quickly, who are developing all this will be TU Delft with the advice of ITU Copenhagen, because we want to have our quality. Where is Andre? It's missing. Okay, he's supervising us as the quality expert in ROS-Industrial, so that we do things that work properly. We will have Universidad Politécnica de Madrid, the Autonomous Systems Lab, working on the ontologies needed to represent these different models, functional configuration, etc. We will have Bosch contributing their system modes that they are creating within the Ofera project and integrating now here in, for the navigation. And we will have the Intelligent Robotics Lab of Universidad Rey Juan Carlos that are contributing to the navigation too, to create these pilots. So a bit about meta modeling. So we are going to be basing our system on a set of meta models, and this comes with some nice properties. Of course, modeling is complex. It requires an additional effort, but actually that pays off the moment you do things more than once, basically. And the moment, you want to have additional tools within your project. So one nice thing is that we can use different tool sets to define our system. So we can compose our navigation system directly using models and then get the associated code, but also tools that validate those. So we will be using the tools that the RobMoSys has already been developing based on the eCore and Eclipse, with associated tools to create and validate your applications. But also we will be, and this is the nice thing of formally using meta models, we will be integrating also ontological tools, basically, which allow for other kinds of verification of system properties. And an example of how these different languages and different models can enhance the verification and validation of your system. I think tomorrow my colleague in ROS-I, Nadia, here at Fraunhofer IPA, will give another presentation using similar models, actually, that we probably will contribute to in her presentation ROS model tomorrow morning. So to wrap up, MROS means Metacontrol for ROS systems. I hope you got kind of an idea of what Metacontrol means, and the idea is to use models at runtime to drive architectural adaptation and have more reliable autonomous systems. That was all. I think it was short. Thank you very much for your attention.